Hello everyone, welcome to my talk on the message complexity of distributed graph approximation. This is joint work with my co-authors Fabien, Shreyas, Gopal and Peter. I am Sriram Pemmaraju from the University of Iowa. I'll start by stating our main result quickly. In this paper we show that exactly solving classical graph optimization problems, namely maximum matching, minimum vertex cover, minimum dominating set, and maximum independent set in a distributed setting requires cubic messages, cubic in the number of vertices. This lower bound is tight. Furthermore, even if we allow a small amount of approximation, these problems can be solved using quadratic messages. And we show that this upper bound is also tight. As far as we know, these are the first cubic in n message complexity lower bounds for graph problems. Usually, these types of lower bounds are quadratic in n or linear in the number of edges. I also want to highlight the sharp separation between the bounds for exact solution and the bounds for approximate solution that we show. We work in the standard Conges model of distributed computing. In this model, we are given a graph that serves as both the input to our problem and the underlying communication network. We assume that vertices in the graph are processors with unbounded computational power. In fact, this is the reason why we are able to talk about solving NP-complete problems exactly. The edges in the graph are communication links and small messages are communicated over these edges. Computation and communication proceed in synchronous rounds. Basically, all processors have access to a global clock, and with each tick of this clock, processors receive messages sent to them at the previous clock tick. They perform local computation and send possibly distinct messages to neighbors. Processors also have unique IDs that are drawn from a space that's polynomial in size. This means that IDs can be represented in order log n bits, and a constant number of IDs can be communicated in each message. Now let me define the notions of message complexity and round complexity more precisely. The message complexity of an algorithm in the Conges model is the total number of messages sent over the course of the algorithm. And the round complexity of an algorithm is simply the total number of clock ticks it takes for the algorithm to complete. And these notions, message complexity and round complexity, defined for algorithms, can be extended in a natural way to defining the message complexity and round complexity of problems themselves. I want to emphasize here that round complexity has been the primary focus of distributed computing, and problems are understood from the round complexity point of view far better than from the message complexity point of view. To emphasize that a lot of research has been done on the round complexity of distributed approximation in the Conges model, let me present a brief case study on the minimum vertex cover problem. Due to a result by Sensor, Hillel, Khoury and Paz, it is known that solving minimum vertex cover exactly takes quadratic rounds. However, minimum vertex cover can be approximated quite efficiently. 2 plus epsilon approximation can be computed in just under log delta rounds, where delta is the maximum degree of the graph. Even a 2 approximation can be computed deterministically, in fact, in polylogarithmic rounds. Much less is known about the message complexity of minimum vertex cover, and this is the gap that our work aims to fill. Now, the situation is similar for the other 3 problems that we focus on also. One might ask why we care about message complexity. Isn't round complexity a sufficient measure? So here I provide 2 important reasons to consider the message complexity of distributed algorithms. The first is that one way to design distributed algorithms in models of large-scale cluster computing, for example, the MPC model, is via simulation of Conges algorithms. Now, for simulating Conges algorithms efficiently in these models of large-scale cluster computing, not only do we need the congest algorithm to be fast, that is take few rounds, but we also require that the congest algorithm use very few messages. Another motivation is that in ad hoc sensor networks, conserving energy is an important goal, and sending and receiving messages requires quite a bit of energy, and so we want to conserve the total number of messages that are sent and received. Theoretical computer scientists may be quite familiar with the notion of communication complexity and might wonder how communication complexity differs from message complexity. At a high level, in both cases, the goal is to measure the number of bits exchanged in solving a problem in a distributed setting. However, there are some fundamental differences in the underlying models, and this leads to differences in the bounds we obtain. In communication complexity, the input graph is completely dissociated from the underlying communication network. So, for example, in two-party communication complexity models, the communication network is just an edge, whereas in the multi-party setting, the communication network is a clique. In the congest model, the input graph is exactly the same as the graph on which communication is occurring. Now, another difference is that in the congest model, processors have access to a global clock because we are in the synchronous setting. And so they might be able to use the clock in fancy ways to save bits, for example, conveying information through silence. On the other hand, in the standard communication complexity model, there is no access to a shared clock. The setting is completely asynchronous and does not permit any encoding tricks using clock ticks. I am now ready to restate our results more completely and more precisely. Basically, this table shows all our results, all of which apply to the congest model, though some of our lower bounds even apply in a stronger model. I first want to draw your attention to the fact that while we have cubic lower bounds for exactly solving minimum vertex cover, minimum dominating set, and maximum independent set, we don't have a cubic lower bound for maximum matching. And in fact, we suspect that maximum matching may have a quadratic message upper bound. I also want to mention that these cubic lower bounds are only for algorithms that take polynomially many rounds. While this is a mild restriction, it is also necessary. We in fact know that if we allow exponentially many rounds, it's possible to solve all of these problems in quadratic number of messages. I now want to emphasize that the quadratic lower bounds for approximate solutions are actually quite strong in some ways. They apply to algorithms independent of the number of rounds that these algorithms take. They also apply to algorithms that use messages of unbounded size. So they apply not just in the congest model, but in the so-called local model in which messages of unbounded sizes are allowed. Finally, I want to draw your attention to our upper bound results in the last column. Here we show that if our input graph is an Erdos-Renyi random graph, then we can approximately solve these problems using just a linear number of messages. In the rest of my talk, I'll sketch the proof for the cubic message lower bound for exactly solving minimum vertex cover. The specific result is as stated in this slide. Our proof is based on the technique used by Sensor Hillel, Khoury, and Paz in the paper cited below, in which they show a quadratic lower bound on the number of rounds for exactly solving minimum vertex cover. This proof uses a reduction to the well-known two-party communication complexity problem set disjointness. Specifically, this proof starts with a lower bound graph construction given two binary vectors x and y, each n squared bits long. They construct a graph gxy with n vertices. Now the vertices of this graph are partitioned into two sets, Vx and Vy, with the property that the edges connecting Vx are completely determined by the bit vector x. The edges connecting the vertices in Vi are completely determined by the bit vector Y, and the number of edges between Vx and Vy is small. That is, the Vx Vy cut is only polylogarithmic in size. Furthermore, and in fact most importantly, this lower bound graph has the property that set disjointness of x comma y is false. That is, x and y have a 1 at a common coordinate if and only if the graph gxy has a small vertex cover. Now, stated differently, this means that if x and y are disjoint, then gxy has a large vertex cover. Now, the threshold separating small vertex cover from a large vertex cover is not important at this point, and I just call it C of n and leave it unspecified. Once the reduction sketched in the previous slide is in place, then the rest of the proof pretty much follows along standard lines. The next part of the proof involves a simulation of a congest algorithm in the two-party model. Specifically, let A denote an algorithm that solves minimum vertex cover exactly in the congest model running in T rounds. Knowing the input X, Alice partially constructs the graph gxy. In particular, she knows all the edges incident on nodes in Vx. So she attempts to simulate algorithm A on the nodes in Vx round by round. Similarly, Bob attempts to simulate algorithm A on the nodes in Vy round by round. From time to time, algorithm A will require a node in Vx to communicate with a node in Vy or vice versa. And when this happens, Alice and Bob need to communicate with each other. It then follows that the total number of bits exchanged by Alice and Bob is T times the size of the cut, Vx Vy cut, times log n. By combining the reduction and the simulation from the previous two slides with the celebrated lower bound on the communication complexity of set disjointness even for randomized Monte Carlo algorithms, we get the quadratic lower bound on the number of rounds needed to solve minimum vertex cover exactly in the congest model. Note that the reduction and the simulation results together imply that Alice and Bob can solve set disjointness with a communication complexity of T times polylog n bits. Then, using the set disjointness communication complexity lower bound, we get a nearly quadratic lower bound on T, the number of rounds needed to solve minimum vertex cover exactly in the congest model. Note that the fact that the Vx Vy cut is small, specifically polylog n edges, is quite critical for this argument to go through. Suppose we want to use this proof approach to produce a message lower bound for exact minimum vertex cover. So the round complexity lower bound argument that I just described, it glosses over the fact that in the congest model, algorithms have access to this global clock and can do fancy things with clocks that Alice and Bob can't quite simulate because Alice and Bob live in an asynchronous world. So for example, nodes in the congest model can partition kind of time into blocks of k slots and then can send a single bit per block to convey log k bits of information. Which slot this particular bit is sent in conveys this information. Now, this is not a problem for the round complexity lower bound just presented, because Alice and Bob can actually maintain and communicate an explicit counter with each other. This takes an additional t times log n bits and doesn't change the rest of the calculations. However, this does not quite work for the message lower bound argument, and we need a more sophisticated way of getting around this problem. We deal with this issue by first considering the synchronous version of the two-party communication complexity model. This is identical to the standard two-party model, except that Alice and Bob now have access to a shared clock. Now, working in this model, Alice and Bob can perfectly simulate the Congest algorithm A. We then appeal to a result that's implicit in a paper by Pandurangan, Peleg, and Squizzato, showing how much help Alice and Bob can get by having access to a clock depends on the number of rounds the protocol executes for. And specifically, if the protocol executes for R rounds, we can hope to reduce the communication complexity of the synchronous protocol by an at most log R factor compared to the asynchronous protocol. This immediately implies that if we restrict ourselves to algorithms that run in polynomial in n rounds, then we just lose another log n factor in the simulation. Now, putting together the reduction and simulation from the Sensor-Hillel, Khoury and Paz paper, along with the set disjointness communication complexity lower bound and the synchronous communication complexity simulation theorem just mentioned in the previous slide, we get a quadratic lower bound on the number of messages needed to solve minimum vertex cover exactly. To amplify this quadratic lower bound, to obtain a cubic lower bound, our high-level idea is to simply stretch the lower bound graph. This is visually depicted in this slide. The high-level idea is that since we've shown that at least a quadratic number of messages need to cross the cut, then if we can stretch this cut to be linear in length and still maintain the connection between set disjointness and vertex cover size, then we would be done, because the quadratic messages would now have to each travel linear in n distance. Now, our key contribution in this paper, or in this proof specifically, is to show that we can actually do this. So far, I have avoided showing the actual lower bound graph construction, but here is a glimpse of the original lower bound graph along with a stretched cut. In the original lower bound graph, the graph in the leftmost gray block is connected via a small cut to the graph in the rightmost gray block. We now stretch this cut by inserting the vertices in the gray columns that you can see in the middle. We insert roughly n over polylog n such columns, each containing log n vertices. Given this stretched lower bound graph, we need a slightly new simulation. Specifically, Alice and Bob agree on a randomly chosen cut, and Alice simulates the vertices to the left of this cut and Bob simulates vertices on the right of this cut. The key observation is that if the algorithm A that Alice and Bob are trying to simulate, if it uses little o of n cubed messages, then lots of the cuts will have little o of n squared messages passing across them. This means that with pretty good probability, Alice and Bob will pick a cut over which little o of n squared messages pass. We can now combine the various ideas just discussed to obtain our final result, specifically combining the new reduction involving the stretched lower bound graph, the new simulation just mentioned, the set disjointness communication complexity lower bound, and the synchronous communication complexity simulation theorem. Together, we get the promised cubic in n lower bound for exact minimum vertex cover. And this completes the sketch of our proof. Now that the proof sketch is complete, I want to place this result in context a little bit. The lower bound is trivially tight because it takes cubic number of messages to send the entire graph to a single node, at which point that node can compute minimum vertex cover locally. If we allow even a small constant factor approximation, then minimum vertex cover can be solved using quadratic messages, using the ball growing approach. We then show a matching quadratic lower bound for approximately solving minimum vertex cover. We are excited about this result as well, but you'll have to read the paper to learn more about it. Our work raises a number of questions, some of which are listed here. The most prominent of these, at least in our minds, is the message complexity of exact maximum matching. And we hope to make progress on this. Maybe others would be interested as well. And I'd like to end the talk by thanking you all for your attention.